do in the class. In that cases, you can come and ask your questions. Yeah. Okay. Right.
Thank you. Thank you.
Yeah. Okay. All right, let me maybe remind you what we did last time. So a quick recall. We were talking about the solutions of some certain type of differential equations. This is first order linear differential equations. In that case, we had integrating factor. Let me remind the integrating factor. Okay. This is lecture 3, by the way. So we had something like this: y prime plus px y is equal to q of x. Okay. And integrating factor was something like this: a function mu, it's given by e to the integral p of x dx. Okay, so you compute this integral and find the integrating factor. Then this differential equation becomes, let's call this star. Okay, and star becomes basically this equation: d dx mu of x times y is equal to q of x times mu of x. And by integrating both sides, we solve y, right? So integrate both sides. And we get something like this: mu of x times y is equal to integral of q of x mu of x dx, and we simply find y from here. Okay, that was what we did last time with a couple of examples. Today,
sorry,
yeah,
I was going to summarize. So we're basically trying to, in the star equation, we're basically trying to get the left side to resemble mu of x times y's derivative.
Right. It's basically left-hand side is derivative of one function only. Yeah.
That's why we got the mu in that way. Just cancel out a px.
Right. We had a mixed term, and we get rid of that mixed term by choosing mu like this. Yeah. Okay, good. All right, very good. Well, of course, this only works in the case of we have first order linear differential equation. So we may have different type of differential equations, nonlinear differential equations. In that case, we have different methods. And here, first, we will talk about separable equations. So this is 2.2 in the book, separable equations. Okay. Well, a separable equation is like this: dy dx. The first derivative, again, it's the first order differential equation. The first order ODE is separable if it's of the form okay, if it's of this form, well, again, we have first order, and it looks like basically a function. Maybe let's take this down a little bit. On the right hand side, we have two functions like this: q of x over p of y. Did we talk about already this? No, we didn't. Okay. Okay. Yeah.
Sir, I'm checking my past notes. It seems like we covered this before.
Oh, sorry. We did this. I'm sorry.
I was like, for a moment, I thought we were gonna link to something new from here, so
No.
I had to tag along.
Yeah, that's my mistake. Sorry about that. We already talked about this, right? We talk about separable and this integrating factor and so on. Yeah. Now, next thing is we will talk about homogeneous equations. Okay. Now we'll talk about this homogeneous equations. So this is now something new. Homogeneous equations. Okay, what's a homogeneous equation? Well, a first order ODE is homogeneous if dy dx is equal to f of y over x. Okay, so basically on the right hand side, it's a function of two variables again, x and y on the right hand side, but you can write this as a function of one variable. The variable is y over x. Okay, sort of. We will do examples and you understand this better. Well, in that case, how do you check right hand side whether this is homogeneous or not? The easiest way is not that. If you have a function f of x phi is homogeneous and it can be written like this: f of y over x. Y over x is like one variable. Okay. If you have this, then you have what? You have basically, let's multiply both variables with lambda. Okay. F of lambda x. Lambda is any constant. Lambda y is equal to, let's see what we get. Well, when you multiply this with lambda, then you get f of lambda y over lambda x. Then you cancel out the lambdas here, and we get f of y over x, which is f of xy again. So basically, this is a nice way to check that right-hand side gives you a homogeneous differential equation in this case, when you multiply with an arbitrary lambda here for any lambda real, okay? So you multiply with an arbitrary lambda and you get the same function at the end, okay? In that case, if you have this, in that case, you have homogeneous equation, and we have a nice method to solve homogeneous equation. We replace y over x with another unknown, let us call v, okay? And we make our homogeneous equation separable and then solve it. Okay, so let's do an example and see what we do in that case. Let's say we have dy dt is equal to t plus y. First of all, is this homogeneous? Well, this equation is not a homogeneous ODE. It's first order ODE, but it's not homogeneous because right-hand side, it's f of ty, okay? But you cannot write this as like f of y over t, because if you multiply with lambda, f of lambda t lambda y is equal to what? Lambda t plus lambda y, but this is not equal to f of xy in general, right? Because f of xy is t plus y. So you see here, this is not a homogeneous equation. Thus, let's call star is not homogeneous. Still, you can solve this equation. How do you solve this equation, for instance?
Integrate both sides.
You can integrate both sides. Well, you cannot directly integrate because on the right-hand side we have a function of y. But we have, this is a first order linear differential equation. So you can use the integrating factor, right? Right. So we have one answer here, integrating factor, right? So you take this to the left-hand side and find the integrating factor and do what we did last time, okay? We can solve it. Using integrating factor. I will not do it. You can do this yourself. Okay. Let's give another example. So this is not homogeneous. Let's give an example of a homogeneous differential equation. In that case, right, p of x is equal to -1. Okay, in that case, p of x is -1, and you find mu and so on. Great. All right. Well, let's look at this one. Dy dx is equal to y plus 2x over x. Now, is it homogeneous? Well, this is homogeneous because you can write homogeneous since you can write this as y over x plus 2x over x, which is 1. So you see here, this is a function of y over x. If I say y over x is, for instance, v, it is v plus 1.
So we're essentially looking for if the function is a function of y over x, or
Right,
if
right.
lambdas can cancel each other out.
Right, exactly, yes.
By the way, yeah, it is too. Chat's saying.
Okay, isn't it 2? Probably, yeah, right. Thanks. Oops. 2 here. Yeah. So you see, this is a function of basically y over x. You can think of like this. Okay. Here f is like x plus 2, okay, or u plus 2, or v plus 2, whatever. Well, how do you solve the equation in this case? Well, to solve the equation, let's put here star, okay, or same here, star. What we do is basically we change a variable y with y over x with, let's call it v, okay? Now we will write everything in y, in v instead of y. So we will get rid of y and write everything in terms of v. So from this, y is equal to x times v, okay? We need y prime. Y prime is equal to, we use the product rule here. Derivative of x is 1 times v plus x times v prime, okay? There's one question in this type of the equation, homogeneous equation, the coefficient of y over x, should it be 1? No, it doesn't need to be 1. Okay, we could have, for instance, 5 times y over x plus 2 times x over y. Okay, as long as you write everything in terms of y over x, that's fine. It doesn't need to be 1, the coefficient. Okay, so basically we get this y prime. Well, from the start, y prime is what? Y prime is from here. It's equal to v plus 2, okay? Because this is v. This is now v, okay? Okay, there's a good question. What is v? V is a function of x, right? Is a function of x, okay? Y is also a function of x. So x is the variable, x and y and v are the functions. We get rid of y and introduce new function v, okay? Dependent variable. Well, from here, we get rid of this v and v here. So what we get is basically v prime is equal to 2 over x. So you see, we get a nice function, nice equation. This star becomes a separable equation. Well, this is basically dv dx. You can write it like this. So from here, v is equal to 2 times ln x plus a constant. Well, now we return to the original variables. So y over x is v, right? Which implies basically y over x is equal to 2 times ln x plus c, and y is equal to 2x ln in absolute value of x plus c times x. C is a real number here. C is any real number, okay? So this is the general solution of star. All right, any question with this?
Can you go over why
y over x?
B'nin türevinin neden 2 bölü x olduğunu tekrar açıklayabilir misin? I wasn't able to understand.
Hangi kısmı bir daha söyler misin?
B'nin türevinin neden 2 bölü x olduğunu bir daha
Şu
açıklayabilir
mu?
misin? Bir sonraki ama evet o da dahil.
Well, what we did here is we used this one, okay? So y is a function of v is a function of x, so we get y is equal to x times v, and we use product rule. So derivative of left hand side is y prime here, okay? And derivative of x times v. V is a function of x, so we use the product rule. Derivative of x is 1 times v plus x times v prime. So here we use product rule. Okay.
Okay, now I understand. Thank you.
Yeah, great. And we use also here left-hand side of the equation, because this is y prime is equal to v plus 2 in the first equation. So we use this and we get rid of v's and so, okay? Any other question? All right, let's do another example. So let's solve this one. Dy dx is equal to x squared plus 3y squared over. First of all, this is not a linear equation because we have y squared, right? When you have y squared, it's not linear anymore. So you cannot use integrating factor and those sort of things. And it's not a separable equation because the top depends on 2 variables, bottom also depends on 2 variables on the right hand side. But it is homogeneous. Let's call this f of x, y. So what we can do is we can write this as this. So x over y, 1 over 2, plus, like this, plus 3 over 2 y over x. Okay. Well, let's also call now here y over x is v. Then, as in the previous case, y is equal to x times v, which implies y prime is equal to v plus x times v prime, product rule again, and this is equal to from the equation here. Okay. 1 over 2 v plus 3 half
So
there is something wrong here, right?
1 over 2v, isn't it supposed to be 1 over 2, 1 over v?
Yeah, right. 1 over 2, 1 over v, right here. Yeah, thanks. Here and this, right? Okay. 3 half y over x. We have x over y is 1 over v, okay? So we get that. All right, let's so we basically get rid of in this equation here, we get rid of y, okay? We write everything in the v. So let's organize this. X times v prime is equal to 1 over 2v plus, we take v to the other side, it's v over 2, okay? And let's divide both sides by x. Or maybe let's keep it like this first. this is equal to what? Let's equalize the denominator. So it's going to be 1 plus v square over. So it may basically be multiplied this with v, okay? 1 plus v square over 2v, okay? Well, from here, you can write like this. This is dv over dx, okay? So what we get is like, or maybe let's write like this first. X times dv over dx is equal to 1 plus v squared over 2v. It's a separable equation now. Okay. So it's going to be dv, maybe let's like this, 2v dv over 1 plus v squared. Let's integrate this. On the right hand side, we have dx over x. So we cross multiply, sort of, okay? Dx over x and integral. Well, the nice thing is these integrals are easy to compute. Left-hand side is basically ln 1 plus v squared, right? You can do the basic substitution to do that. Right-hand side is ln in absolute value of x plus a constant. So we get, simply take the exponential both sides. We get 1 plus v squared is equal to e to the ln in absolute value of x plus c. So it's going to be x times e to the c. Or simply, we need to go back to the original variables, which is y, original variable y. So what v was y over x, 1 plus y squared over x squared, v is y over x. So it's equal to absolute value of x times, instead of here e to the c, you can say this is c tilde. It's another constant, right? E to the c is a constant, so you can replace with c tilde, another constant. C, you don't need to do that, but it's it looks better. So from here, y is equal, maybe let's keep it like this. It's because we have two solutions, so this gives the solution in the implicit form, okay? Gives the solution in implicit form. Any question with this? Okay, there is one question. Could we integrate right-hand side 1 over 2v and v? Well, the thing is, you cannot do it. If you do that, what would you do with this one, v prime? Okay, that's another problem, because left-hand side depends on two functions, so it's not going to be easy, right? If you integrate this side first, there's v prime here, so that doesn't make sense. There is another question. Could we write this explicit solution? You can write the explicit solution, but there are two solutions. You need to write both, okay? But you don't need to write the explicit solution in these cases, okay? The implicit solution is fine. Any other question? Here I would say maybe let's include here C tilde is any real number, okay? Question, comment? How do we use separable equation? Here, this equation is separable. It's separable equation, right? On the right-hand side, you take x to the bottom here. And then it's gonna be like a function of v over function of x. So it's a separable equation, okay? Any other question? Well, okay, there is one question by Ozan. Well, this is actually what we did. We did the same thing. So you can do it, yeah. Okay. This will work, of course, because it's the same thing. We equalize the denominators to see this integral easy, okay? So. Well, the thing is, when you write like this, maybe I will explain here. When you say that this dv over 1 over 2v plus v over 2, how do you integrate this? You cannot separate the integral here, okay? Because this is not like a plus b, it's like 1 over a plus b, okay? So this is not the same as dv over 1 over 2v plus dv over v over 2. They are not the same, right? Maybe you did this wrong. Okay. All right. Any other question? All right.
Hocam ben bir şey sorabilir miyim?
Tabii.
Bu mutlak x çarpı e üzeri c tam olarak nereden geldi? Orayı kaçırdım da.
Well, it follows from here, e to the this, okay? So this is basically e to the ln x times e to the c, right? But e to the ln x is x.
Tamam,
Lower
teşekkürler.
and exponential, they cancel each other, okay?
Teşekkürler.
Okay, great. Any other question?
Yeah, can I ask a question?
Sure.
So when we face such an examples, so do we need always to write y divided by x is equal to y and always do the same steps, or we can do somehow something else?
If it's in first order and separable, this method always works. Yeah, it always works. Yeah.
Okay, thank you.
Yeah. All right. Let's move to a different topic. This is modeling 2.3 in the book. Modeling with first order ODE. Well, now we will consider some real life problems, and we will try to solve these real life problems using first order differential equations. Well, there are many different types of real life problems you can try to solve. Here we will touch some of those, but you can find more in the book. There are many examples and suggested problems as well. So to solve problems with ODE, what we need to do is first Of course, the first thing is you read the problem carefully. I assume you do this. Well, next thing is determine dependent and independent variables. Basically, what is the variable? What is the function? Okay, you're trying to solve. Independent variables. Okay, next, relate the rate of change in the problems. Rate of change is like the derivative, right? Derivative of y, derivative of the function. So you will relate derivative of something with derivative of something else. Relate the rate of change in the problem. And finally, find initial conditions so this will be given in the problem and solve the initial value problem. So it becomes an initial value problem at the end, and you solve it with the techniques you learned here. You can try, this integrating factor if the separability is easy. If it is not, but homogeneous, then you apply this homogeneous technique to make it separable, then solve it. Let's do some examples. So this is application 1. And it's Newton's laws of motion. Second law of motion. Well, basically we have a mass and we push forward this mass with a force. Okay, and so this is the force acting on this object, and let's call the initial position y0, which is the position at the time 0. Okay, then you move it and it comes to that point, let's say here. Okay, so this position is now y is equal to y of t. So this is the position of the object at the time t, yt, let's write here, yt. It's the displacement, of the mass. So its derivative, y prime t, gives what? We know this from physics. The derivative of the displacement function is the speed, right? It's v of t is the speed of the mass. And second derivative, or derivative of speed or velocity, whatever, a of t, which is v prime t. This is the acceleration. Then Newton's law, second law, says it's the total force on the object is equal to m times a. Here, m is the mass of the object, okay? Mass, so it's like given usually in kilogram or gram or whatever. And the Newton's second law says it's equal to m times a. What is a? A is acceleration, and it's given by dv dt, the derivative of velocity with respect to time. And it's also written as v was, remember, the derivative of y, the displacement function. So it becomes d square y over dt. Right? So the total force, let's write here, total force is equal to this. Well, let's do an example. An example. Consider an object falling without air resistance. So there is no air resistance. We have such a picture. We have a mass. Okay. And this falls down. Okay. Well, the first position at this level, let's call it y0. It's the position at the time 0, okay? And there is a gravitational force F is equal to m times g, right? G is the gravitational constant. This is gravitational. G is the gravitation constant. It's close to 9.8 meter per second square. And yt here, let's say it moves to it down to this level, and this is yt. It's the position at time t. Is the position of the mass of the object at time t. So we will write a differential equation which involves y and try to obtain the displacement y in terms of this quantity here, g. Okay. So there might be an initial velocity. If there is an initial velocity, let's say v0 is v of 0 is the initial velocity. of the object. Well, of course, if you drop this mass object without any force, it's basically zero, right? Initial velocity is zero, but you can do this with a force, and then there is an initial velocity in that case. So let's write the initial value problem here. Well, remember that there is this equation. Let's call this star here, okay? So this says you can cancel out here, for instance, or maybe let's, okay, right, like this. The total force is mg, right? It's F is equal to mg. At the same time, this is equal to m times a. A is the second derivative of y. That was the acceleration, okay? Remember, this was a of t, the acceleration of the object. You can cancel out m's and you basically get what? So the initial value problem is this. D square y dt is equal to g. G is the constant, gravitational constant. What are the initial values? This is the second order differential equation. So we have two initial values. The first one is y0 is y sub 0, it's a constant, the initial position. And the initial velocity is v0, it's the derivative at 0, right? It's v sub 0, all right? So we will solve this initial value problem to get the displacement function. Right, thanks for this. There's t square here, second derivative. So let's solve this differential equation quickly. It's an easy differential equation. You integrate basically left-hand side and right-hand side. So it becomes dy dt is equal to g times t plus a constant, let's call this c1. C1 is a constant. Differentiate this again, and it becomes y is equal to g t squared over 2 plus c1t plus c2. So what are c1 and c2? Well, y0 is equal to y sub 0. When t is equal to 0, it becomes c2. So we get that c2 is equal to y0. What about y prime? Y prime 0, here we can use this one. Okay, so y prime 0 is equal to, on the one side, it's v0, the initial velocity, and from the equation here, it's basically 0 plus c1. So we get that c1 is equal to v sub 0. Now let's combine all this and write the displacement function. So y of t is basically g times t squared over 2 plus c1t. C1 is v0, the initial velocity times t, plus c2. C2 is y0. Okay, this gives the position of the object falling. Any question with this? All right, let's give a break here for 10 minutes. So let's meet at 11:45.
Quick question.
Yeah.
Let's say G or A for a general case is not a fixed number. It's just some sort of a function or something else.
G is fixed, but A is not fixed. It's like when the object is speeding, then acceleration is getting larger and larger, right?
Yeah, A is not fixed.
A is not fixed. It depends on time. If the speed is constant or speed is linear, let's say, then in that case A is fixed. But if you speed up so fast, then the acceleration is not constant.
Yeah.
Okay. All right.
In that case, what do we do? Like, for A case, instead of G, we plug in A, for example.
No. Here, this is the general case. In this case, G is always constant. It's the gravitational constant. It is the gravitational constant which comes from Earth.
So this applies for just this case, free falling.
Free fall, or if you apply some force or air resistance, you still have gravitational force plus something else.
Basically, wherever the acceleration is a constant number, no changes.
No. What I'm saying is, let's say there is also a resistance here, and there is another force here. Then you find the total force.
Yep.
Okay, and the total force is equal to, anyway, it's equal to m times the acceleration. Because acceleration is not constant. It depends on how fast the object is moving. So this right-hand side of the equation is always same. It's always this, but left-hand side here, this may change, okay?
Okay, I got it.
Great. All right, see you at 11:45. All right, welcome back. So let's continue with another application. Do you have any questions so far? So we have application number 2. Newton's law of cooling. Well, here T is time as usual. Ts, by Ts, we note the temperature of the surrounding system. So for instance, temperature of the room in some cases, it might be temperature of some other things. And by T, which is a function of small t, it's the temperature of the object at any time t. Temperature of the object at any time t. And K is the cooling or heating constant. It's a constant, depends on the heating or cooling object here, okay, source here. Then Newton laws of cooling says you can find the temperature of the object by using this differential equation, first order differential equation. The derivative of T is equal to minus K times T minus Ts, okay? Well, it's the separable equation, as you see here. So we can solve this equation easily. Let's do an example. So suppose a thermometer is placed in a room with constant temperature . Constant temperature . Ts, which is 10 Celsius. Okay, let's go over this again. There's one question. So we have in this sort of application, we have an object in a surrounding system. Ts denote the temperature of the surrounding system, for instance, temperature of the room. And in this example, for instance, we place a thermometer in a room. So the room temperature is the surrounding temperature. It's constant, 10 Celsius, okay? And T here denotes the temperature of the object, okay? And K is a cooling constant. It's a constant. You will find out this constant using the initial values, okay, later. And that's it. So we have this example. We have a thermometer placed in a room with a constant temperature, 10 Celsius. Initially, thermometer shows (22 Celsius). Okay, it shows 22 Celsius, and after 2 hours, it shows 16 Celsius. Determine the value of the thermometer after 3 hours. Okay, so we know the initial value on the thermometer, which is 22. We place this thermometer in a room, so it's cooling, right? Because room temperature is smaller than the thermometer, temperature of the thermometer, which is 22. So after 2 hours, it becomes 16 Celsius. And the question is, what is the value on the thermometer after 3 hours? Well, let's write the equation by using Newton laws of cooling, the differential equation. So it says basically dt over d small t is equal to minus k times T minus the surrounding temperature. Surrounding temperature is the room temperature, which is 10 Celsius, and it says it's constant. So let's put here 10. Okay, let's put just 10. Okay, so this is the equation. We will try to solve it. We don't know K here. Well, it's a first order differential equation. The initial values are, there is one initial value, another one is given as well, and we will use two initial values to find two constants. Basically, one is K, the other will come from the solution. So T0 is 22, and T2 is, after 2 hours, it is 16. And what the question is, what is T3, right? So this is the question. So let's solve this initial value problem. It's a separable equation. You can write it like dt over, take all the capital T's on the left-hand side, t minus 10, and integrate on the right-hand side, minus k dt, and integrate, okay? Well, left-hand side is basically logarithm, right? Natural logarithm, ln t minus 10 is equal to minus k times ln t. You don't need an absolute value here because t is the time. T must be positive, right? Time is always positive, so you don't need an absolute value here because t is positive. Time is always positive, right? Well, from this, let's find out capital T, take the exponential of both sides, we get t minus 10 in absolute value. Is equal to
Hocam.
Hocam orası T olacak galiba. ln T değil de.
right, so this should be T, sorry. Oh, wait, then, okay, right. So we take the exponential, we get t minus 10, it's e to the minus k t plus a constant c. Oh, plus c here, sorry, plus c here. Right. It's gonna be e to the minus kt plus c, like this. Well, here we can get rid of the absolute value. The reason is the temperature of the object, T is the temperature of the object, right? It's always greater than 10 because room temperature is 10. It never goes down 10, right? So we can write here without the absolute value because T is always greater than 10. Remove the absolute value because T is greater than or equal to 10 because room temperature is 10, right? So it cannot go down below 10 Celsius. And from here, we get simply T is equal to 10 plus e to the minus k t plus c. Okay, well, let's find out k and c here. T0 is 22. At the same time is 10 plus e to the 0 plus c, which is e to the c. So c is here ln 12. Okay. Well, let's find out k. When t is equal to 2, it is 16, and this is 10 plus okay, there's one question, e to the power c. Can we say, instead of this, can we say c? You can do it. That's fine. You can do that as well, like in the previous example. Ten plus, well, what is t? T is 2. It's going to be e to the minus 2k plus c is now ln 12 is equal to 16. So this tells you basically e to the minus 2k times e to the ln 12 is simply 12. Okay, is equal to 6. Or you can say e to the minus 2k is equal to 1/2. And from here, minus 2k is equal to ln 1/2, which is minus ln 2. So k is equal to ln 2/2. So what we get basically we get the following. T is equal to, maybe let's write it like this. T of t is equal to 10 plus e to the minus ln 2 over 2 times t plus c. C is ln 12, so e to the ln 12 is 12. So basically it is times 12, okay? Any question with this? We're not done yet. We will find t of 3. So t of 3, after 3 hours, it becomes 10 plus 12 times e to the minus ln 2 over 2 times 3. Well, you can basically write this in a simple form. It's like 10 plus e to the ln 2 is 2. So it's like 2 cubed 8. So it's 2 to the minus 3 over 2. Okay. And this is approximately times 12. Sorry, times 12. This is approximately, of course, you don't need to do that, approximately 14. So after 3 hours, it drops to 14, about 14. Any question so far?
Hocam sesim geliyor mu?
Geliyor.
T'yi genel denklemini bulurken 10 artı e üzeri eksi kt artı c dedik ya. Onu e üzeri eksi kt çarpı e üzeri c diye ayırıp e üzeri c'ye yeni bir c assign etsek de aynı
Evet,
sonucu
evet.
buluruz değil mi?
Bulursun, tabii ki bulursun.
Sadece mesela c'yi ln 12 değil 12 bulmuş oluruz ama
Aynen,
sonuçta
aynen.
bir değişim olmaz.
Aynen öyle.
Anladım. Teşekkür ederim hocam. Sağ olun.
Yeah, you could write, instead of here, you could write, where is it? Yeah. In the solution, instead of writing like this, you could write e to the minus kt times c, or c tilde, whatever, because e to the c is another constant, and you can go ahead with that. You will get the same, okay? Any other question? All right, let's do another application. Application number 3. Now we have some mixing problems. Well, what we do here is we have a tank like this, and we fill in here with some water, let's say. It's a mixture, okay? And there is a mixture here. And at the same time, the mixture flows out from here, okay? So there is a mixture flows in and flows out at the same time. And this mixture contains some chemical. Here, chemical is, it can be salt, sugar, or a real chemical, okay? Depends on the problem. So let's write here. There is a concentration of, so this concentration is C1 concentration of the chemical, okay, C1 gram per liter flows in at a rate let's say R1, so these are some numbers, liter per minute, okay? And at the same time, here, some concentration of C2 gram per liter flows out at a rate R2 liter per minute. So R1 and R2 are given, okay? And the concentration of the chemical in the fluid is given as well by C1 and C2. And what we're going to find is we will find after a certain time what is the quantity of the chemical inside this mixture. Okay, so here T is time again. QT, it's right here. QT is the amount of chemical in the tank. This chemical can be sugar, salt in the tank at any time t. Well, Vt is the volume of the mixture. It's volume of the mixture. Of course, the volume may change by time, depending on the mixture flows in and out. Okay, volume of the mixture at time t. Well, what is, for instance, here C2? C2 is the concentration of the mixture flows out, right? So you can write this equation for C2. C2 is basically, let's say at time t, you have that much Q2 amount of chemical, and the volume is Vt. The volume is Vt, right? So this is basically the gram per liter. Okay, so you can use this formula to write C2. This is one formula we will use. But the main formula is here. So basically, we will try to find Qt. So to find Qt, we will use this equation. The change in the amount of the chemical Qt by time t, it's basically rate in, right? So there is a chemical flows in. So we have rate in, the change in the solution, and rate of change in the solution, and some chemical flows out, solution flows out. So we need to subtract this one. So this is rate out. Okay. So what are the units here? The units must be dq over dt. dq is, well, q is basically gram. T is time. So this is like gram per minute, for instance. Depends on the problem. Sometimes it's kilogram over second, kilogram over minute. But anyway, it's like some mass over time, okay? And gram per minute again. So what are this rate in and rate out? Well, it's basically rate in is, so let's first compute this rate in. Well, remember that here concentration of C1 gram per liter flows in at the rate of R1 liter per minute. So if you multiply this two, basically you get rid of the liters. Okay, it's gram over minute. So this is rate in. Okay, so C1 C1 times R1 gram per minute minus what is rate out. So some mixture flows out here, right? And what is the rate of this flow? Well, we have concentration C2 gram per liter, and it flows out at the rate of R2 liter per minute. So if you multiply this two, it becomes C2 R2 gram per minute. Gram per minute, okay? So this is the equation we will use to solve this sort of problem. Okay. Well, let's do one example. Of course, there are going to be initial values. The amount of the chemical at the beginning, for instance, it can be given. Then using this initial value and differential equation, first order differential equation, we will find the amount of chemical inside the solution. So at time t, at t is equal to 0 initial time, a tank contains 50 kilogram salt dissolved in 1,000 liters of water. Okay, so the initial amount of salt is given here, Q0, basically, and water containing 100 grams of salt per liter. So this is the concentration of the salt flows in, is entering the tank at a rate of 30 liters per minute. Okay, and that mixture is leaving the tank at the same rate. So basically, it flows and flows in and out at the same rate. And we will find the amount of salt in the tank after a very long time. Okay. So again, we have a tank and there's a water flows in at a rate of 30 liters per minute, and it contains 100 grams of salt per liter, and the mixture is leaving the tank at the same rate, and we will find the amount of salt in the tank after a very long time. That means basically time goes to infinity. Okay. So to solve this, we will write the equation, differential equation. There is one answer. It is 100 times 1000 over 30. Let me see. Nope, it's not. Let's see what we get. No, the thing is, it flows in, okay, but at the side, it flows in and flows out at the same time, right? So the volume is always the same. We have same volume of the mixture, okay? So the mixture, inside the mixture, the amount of the chemical will change by the time. So Q is close, it's 50, but it's not 50. Maybe you did something mistake, some small mistake. All right, we have some guess. Well, anyway, we cannot do it without writing the equation of the differential equation, which gives this, which models this real life problem. So basically, we will deal with such a problem. The change in the quantity dq dt. Okay, so what is q here? Q is basically the amount of salt. Maybe let's write this first. So say qt, the amount of salt at time t, and q0 here, the initial amount is, at the beginning we have 50 kilogram, so it's, well, by the way, unit is kilogram here, so we will write everything in kilogram. So here it is 50. Okay. Okay, there is one right answer. It is 100. Right, the 100 will be the answer. Good. Well, so we have what? We have this equation dq dt is equal to rate in minus rate out. Okay. What is rate in? Rate in is basically it flows in the water containing 100 gram per liter. So it's 100 grams is 0.1 kilogram per liter times 30 liter per minute. So it flows in a rate of 30 liters per minute. Okay, we have this. So this is rate in minus rate out. So rate out is what? Well, we have Q T kilogram in the solution, and it flows out in the same rate. What is the rate here? It's 30 liters per minute. So it's gonna be, well, QT over, what is the volume here? The volume is, so this is the concentration of the mixture flowing out. QT is the gram, and the volume is VT is what? Flows in and flows out. So it flows in and flows out at the same rate, so volume doesn't change. And we have 100 liter of water, so it's always 100, okay? The volume doesn't change. The volume is constant. It's not always constant. It depends on the problem. Okay, if the rate of flow in and flow out, they are different, then the volume may change. Here it's constant. Okay. Times, so this is what? This is kilogram per liter times it flows out at the same rate, so it's going to be 30 liters per minute. Well, basically we get what? We get, let's write in a simple form, dq over dt is equal to 3 minus 3q over 100. Okay. So this is a first order linear differential equation. It's not 1000, 30 over 1000, 3 over 100, okay? So we cancel out the 0. Well, here mu2 is well, we don't even need that. You can do it, but it's easier than that. You don't need here integrating factor because it's a separable equation. It's basically 300 minus 3q, okay, over 100. So you can write this as dq over 300 minus 3q and integrate is equal to dt over 100. Okay. Okay, there is one question why we have here for the rate out Q2 over 1000. So this is C2, the concentration of the chemical salt in the water, and this is R2, okay? It flows out at the same rate, so it's R2, that's why we have this, okay? All right, well, we are almost done here. Let's solve this equation. So we get basically minus 1 over 3, integrate this, it's going to be minus 1 over 3 ln 300 minus 3q is equal to t over 100 plus a constant. And from here, you can do it yourself. Q of t, solve this equation, sorry. Oh, we lost the page, sorry. Well, we lost the page, sorry for this, but we had this. Let me continue with this, okay? So we had Q of t is equal to 100 minus c times e to the minus 3t over 100, okay? So this is the general solution, but it's an IVP, initial value problem. So,
Hocam bundan bir basamak öncesinden devam edebilir misiniz?
tamam, bir saniye. Çok pardon. All right, let's try to share with this. Okay, so we had, let me remind what we had here. We had this equation dq over dt is equal to 3 minus 3q over 100, which is 300 minus 3q over 100, okay? And then you can solve this by integrating the following. dq over 300 minus 3q is equal to dt over 100, okay? And you simply integrate both sides and you get qt by this, but q of 0 was 50. Okay. So basically, this tells you that 100 minus c times, when we plug 0, it becomes e to the 0 is 1. So it is 50. So from here, c is equal to 50. That means basically the amount of the salt here at any time t is given by 100 minus 50 times e to the minus 3t over 100. The question is, after a very long time, what is qt? So as t goes to infinity, qt will approach to where? Well, this will approach to 0 as t goes to infinity. That's why we have qt approaches to 100. Okay, 100 kilogram. After a very long time. Okay. Right. Why we have dq numerator? Well, it follows from here. Why do we have this? Basically, it follows from this over this one is equal to, it's like cross multiply, okay? Clear now? Any question? Any comment? Okay, let's stop here. I will put, of course, these notes with some corrections in the last part. I will rewrite this and put it on Meetbot class. See you on Friday. Bye.
Thank you, hocam. Have a nice day.